5.6, inverse trigonometric functions and differentiation. Recall that you know how to find the angle whose sine is 1/2. By remembering your unit circle values, you know one answer is pi/6. But the sine function is also positive in quadrant 2, so another answer is 5pi/6. Actually, there are infinite answers, since any angle which is coterminal to these angles will also have the same sine value. This creates a problem when we are considering inverse functions, since the sine function is not 1-to-1. Therefore, we must restrict the domain to a specific interval. For the sine function, this interval is -pi/2 to pi/2. Each trig function has its own domain restriction. Now, also, recall that the graph of an inverse trigonometric function reflects across the y = x line. The inverse of the sine function is a new function, denoted by the sine to the -1 of x. We call that inverse sine, or we can also call it arc sine. You will see it both ways, so be comfortable with both. When you are asked to consider only the restricted interval from -pi/2 to pi/2 inclusive, so a closed interval, this is often denoted with caps, but it's called the principal value. Now, notice that if we take the sine function and we restrict it to -pi/2 to pi/2, inclusive, every value for sine function occurs in that interval. And this will pass the horizontal line test, making it 1-to-1. Now notice, what would the inverse look like? Well, you will notice that in this interval, sine is increasing, and we have concave up and then concave down. So arc sine would also be increasing, but the concavity changes, concave down to concave up. Also, the -pi/2 pi/2, which we're used to on the x-axis for sine of x, goes to the y-axis now for arc sine. And the -1 and 1 that we normally see on the y-axis will go to the x-axis. The restricted intervals for the trigonometric functions are sine, restricted to -pi/2 to pi/2, the closed interval. Tangent, the same interval, but it's an open interval. Cosecant, -pi/2 to pi/2, except for where theta is 0, because let us remember, if sine of 0 is 0, cosecant would be reciprocal of that. Cosecant is not defined for theta = 0. Also, cosine theta, cotangent theta, and secant theta must be restricted to 0 to pi. Now, notice that cosine is the closed interval 0 to pi, cotangent is the open interval 0 to pi, and secant is the closed interval 0 to pi, except theta cannot be pi/2. You can look in your textbook for page 372 for graphs of your inverse functions. Recall, there are two classes of functions, algebraic and transcendental. Now, polynomial, rational, and radical functions are algebraic. Your logarithmic, exponential, and trigonometric and inverse trigonometric functions are transcendental. If you recall, the derivative of the transcendental function f of x = ln(x) was f prime of x = 1/x, an algebraic function. Likewise, the derivatives of the inverse trigonometric functions are also algebraic. We're going to look at this diagram right here. We're going to let y = arc sine x. In other words, y is the angle whose sine is x. So if this is the y and my y is the angle whose sine is x, then the sine of y has to equal x, and that would mean, remembering our opposite over hypotenuse, the side opposite this angle would be x, and the hypotenuse would have to be 1. Now, we know the side opposite y is x, the radius is 1, and by using Pythagorean theorem, this side squared, I'm going to call it question mark for a minute, this side squared plus this side squared is 1. Therefore, x squared plus question mark squared equals 1 squared. So question mark squared is 1 minus x squared. So this side is the square root of 1 minus x squared. Now, why is that useful? Because if I want the derivative with respect to x of the sine of y, let's remember, that's going to require chain rule. The derivative of sine is cosine of y times dy dx. And if I have the sine of y equal to x, the derivative of the sine of y gives me this, the derivative with respect to x gives me this, and I can solve for dy dx, which is 1 over the cosine of y, and my cosine of y was the square root of 1 minus x squared. What I wanted to show you is this derivative is algebraic. Therefore, the derivative with respect to x of arc sine x is 1 over the square root of 1 minus x squared for all x's between -1 and 1. Remember, my arc sine on the horizontal axis is -1 to 1. By a similar argument, the derivative with respect to x of arc cosine is the opposite of 1 over the square root of 1 minus x squared. Here is how we do it. The development of the derivative with respect to x of arc cosine x. We're going to draw our triangle. Y is the angle whose cosine is x. So if the cosine of angle y is x, we know that that is adjacent over hypotenuse. So my adjacent needs to be x, my hypotenuse needs to be 1. Using Pythagorean theorem, gives us that this side is 1 minus x squared under the radical. So if y is the angle whose cosine is x, then we can write that as the cosine of y is x. The derivative of cosine is negative sine of y times the derivative of y equals derivative of x is 1. dy dx is -1 over sine of y. So dy dx is the negative of 1 over the square root of 1 minus x squared. All right, if f of x equals arc sine x, find the derivative at 1/2. Well, I know that the derivative of arc sine is this, so the derivative at 1/2 is substitute 1/2 in there, and we get, with all the algebra, 2 over square root of 3. So at 1/2, the slope of my tangent line would be 2 over the square root of 3. A little bit more than 1, because square root of 3 is about 1.7. So 2 over 1.7, a little bit more than 1. Remember that chain rule also applies. So the derivative of the angle whose sine is u is 1 over the square root of 1 minus u squared times du dx, or u prime over the square root of 1 minus u squared. The derivative with respect to x of arc cosine u is the negative of 1 over the square root of 1 minus u squared du dx, or negative u prime over the square root of 1 minus u squared. You need to know these formulas. If f of x is the angle whose sine is the square root of 1 minus x, find f prime. Again, we're going to let our u be 1 minus x to the 1/2. So du dx is 1/2, 1 minus x to the negative 1/2 times the derivative of the inside, -1, which we get to be negative 1 over 2 square root of 1 minus x. Notice we are looking at arc sine u. The derivative of arc sine u is 1 over the square root of 1 minus u squared times du dx. 1 over the square root of 1 minus u squared times du dx. And now we're just going to clean it up. What can we do here? We can see that we're squaring this radical, so that's going to give me 1 minus parentheses 1 minus x when I square that. Okay. This 2 that's here can come in front, and I can put both of these factors in the denominator. This work here, 1 minus 1 becomes plus x, so I have the square root of x times the square root of 1 minus x times that 2 with a negative on top. So I wouldn't leave it like that. I would at least square root of x times square root of 1 minus x, bring those together under the same radical. Now, it is going to be your algebra skills which perplex and torment you on this material. Now, one of the properties you're going to need to know very well is the derivative of inverse tangent. So let's return to the conditions that we used for our proof of sine. Again, we're going to let y equal the angle whose tangent is x. So here's y. We know that tangent of an angle is opposite over adjacent. So if the angle's tangent is x, that means opposite side is x, adjacent side is 1. And we know that 1 squared plus x squared gives me radius squared, so that makes my radius to be the square root of 1 plus x squared. Now, let us find y is arctan x, which means tangent of y is x, and we're going to find the derivative. So the derivative of this side, remember derivative of tangent is secant squared of y times dy dx. Derivative of this side of the equation is 1. Solving for dy dx gives us this. So I have 1 over secant squared of y. Let's remember that secant squared theta is 1 minus tangent squared theta. So secant squared of y could be written as 1 plus tangent squared of y. And I know that tangent squared of y, if the tangent of y is x, tangent squared of y is x squared. So really neat thing, the derivative with respect to x of tangent y is 1 over 1 plus x squared. So we've just proven that the derivative of arctan x is 1 over 1 plus x squared. Now, there is another way to think about this. 1 over secant squared y is cosine squared y. We know that cosine y is 1 over the square root of 1 plus x squared. Cosine of y is 1 over the square root of 1 plus x squared. And so cosine squared of y would square this, which gives us this. Nice little thing. So therefore, the derivative with respect to x of arctangent x is 1 over 1 plus x squared. And by a similar argument, the derivative of arc cotangent of x is the opposite of that, negative 1 over 1 plus x squared. Okay, so the chain rule for inverse tangent, cotangent, secant, and cosecant derivatives are these. Remember, times u prime. These need to be changed to u's in your notes. All right, we're going to find the tangent of the angle whose cosine is 2 over square root of 5. Now, we do not know a unit circle angle whose cosine is 2 over square root of 5, so how are we going to find this without a calculator? Well, I know that if the angle is 2 over square root of 5, that means my side, adjacent, and hypotenuse are in the ratio of 2 over square root of 5. And if I know that they are in the ratio of 2 over square root of 5, then I can certainly find the side opposite. And that's what we're going to do. Here's my triangle. My angle whose cosine is 2 over square root of 5, so my y is adjacent side 2, hypotenuse square root of 5. And this is going to be our x. We can use Pythagorean theorem to find that our x is 1. So the tangent of y is x over 2. And if x is 1, that means tangent of y is 1/2. We didn't even need to do any derivatives there. Okay, what about this one? We're going to take the derivative of y, which is 1 over the inverse of sine x. That is not 1 over sine x. That is the inverse function. So we're going to write that as arc sine. We're going to make fewer mistakes if we think about that as arc sine. Which means arc sine of x to the negative 1. That is a negative 1 used in the way we think it should be used. So y is arc sine of x to the negative 1 power. Well, we know how to take the derivative of that. Negative 1 times the angle whose sine is x raised to the negative 2 times the derivative of arc sine x. Here is this piece times, we know the derivative of arc sine is 1 over the square root of 1 minus x squared, and there's our ugly answer. It's okay, it's ugly. Our last example, notice that is a product. Okay? And if I want to think about my product rule, we don't want to use f because that is our function. I'm just going to call it a and b. Okay? So ab prime plus a prime b. I'm going to let my u be the square root of x, or x to the 1/2. So my u prime is 1 over 2 square roots of x, which is my du dx. So f prime of x is equal to x times the derivative of inverse tangent. There's the derivative of inverse tangent of u, which requires times u prime, plus inverse tangent of u times the derivative of x. And clean up on all four. Page 376 has all the derivative formulas you have to know. That's quite a bit that you've learned up to this point, isn't it? Your TPs, number 7, 11, 17, 41, and 43. See you next time.